Okay. I hope that we are ready to start our class today. Good morning, everyone. Thank you for joining back to our lecture today. So first, a quick check. Is the sound okay? Can you guys hear me clearly?
Yes, we can hear you.
Okay. Well, thank you, gentlemen. So now let's go back to our slides, if you don't mind. We can start now. So this is actually where we were last time. We started to talk about the PN junction. Actually, we would like to take a very short detour to go back to look at the PN junction physics as well as the process inside the PN junction. So if you remember, we talked about actually two things that is very familiar actually from the lecture before. We mentioned that there are two mechanisms for the carrier transport inside a semiconductor. Okay. First of all, there is the drift process. Okay, the drift process or drift current that is coming from the electric field, and then we introduce the mobility concept. Okay, the mobility concept. So essentially, mobility is talking about the velocity of the carriers coming from a certain electric field intensity. Okay, so that is the drift current or the drift process. And the other mechanism for carriers inside semiconductor is the so-called diffusion. Okay, diffusion is coming from the local concentration gradient difference, and from this difference, any kind of carrier species will have the tendency to go from high concentration to low concentration. That is the diffusion process. Okay, so from this process, we can also obtain a so-called diffusion current. That will be proportional to the diffusion constant of this material. Okay, so different material again will have a different mobility, will have a different diffusion constant that will give a different diffusion and the drift behavior and different current behavior. Okay, and then one of the most fundamental equations we need to use to solve any kind of PN junction structure or solar cell structure is from actually the so-called Gauss law. Okay, in the one-dimensional case, in the differential form, we have this equation that is shown here, which tells you that the divergence of the electric field vector will have to equal the space charge density divided by the permittivity epsilon. Okay, so this is actually a very useful equation for us. And in fact, in solar PV, actually we use this equation basically to visualize what is happening inside our PN junction. Okay, inside the PN junction. So let's start from here. So for we from the equation we have here, we know that our starting point obviously is the space charge density. Okay, space charge density rho here. And for the one-dimensional PN junction, actually this the rho distribution is actually very simple. Okay, it's actually very simple. We know that near the n-type, this is the n-type side, this is the p-type side, this is the interface. Near the n-type side, we have a positive space charge. In the p-type side, we have a negative space charge, and the space charge are only within the space charge region. Okay, so if you go far away from the n-type side or the p-type side, basically the space charge is going to be net zero. Okay, so you have a no space charge far away from the space charge region. Okay, and from the in real situation, typically the real space charge density typically will follow the dash profile. Okay, it will follow the dash profile, meaning that we're not going to see a constant space charge density near the space charge region, near the interface. However, this is a little bit difficult for us to solve, which is why typically we will take some approximation to simplify the solving. Okay, we take typically two approximations for solving the PN junction. One is the so-called uniform doping approximation. Okay, the second is actually the abrupt junction approximation. So for let's look at the second one first. For the abrupt junction approximation, we assume that the space charge region will cut off very suddenly, very sharply, actually at the certain point. Okay, that's why you see that we have actually on the left and on the right side we have these rectangular box here, because we assume that the space charge region, the junction basically will cut off here suddenly. Okay, that is the abrupt junction approximation. Now back to the first approximation, the first assumption, we assume that within this box, the doping density is going to be constant. Okay, the doping density is going to be constant. So if the doping density is constant, in the space charge region, then because we know that in the space charge region, the semiconductor will lose all the free electrons or free holes, and therefore the space charge that you are seeing here, essentially, it will equal directly the number of dopants. Okay, it will equal directly the number of dopants. So from the anti side, the space charge will equal precisely Q times the donor. Okay, while from the p-type side, this will equal directly negative Q times the acceptor, which is actually what we are writing here. Okay, so with the uniform doping approximation, because we assume that this is a constant, okay, then in this case, we can simply plot a constant space charge in the space charge region. Okay, so this actually will help us simplify the solving, which means that we're saying that the rho here will be a constant within the box region, within the rectangular region. Okay, so if rho is a constant, then because the slope of the electric field equals a constant, so essentially the electric field should be a linear function. Okay, should be a linear function. So on the p-type side, it's going to show negative slope because actually we have a negative constant space charge. Okay, on the other side we have a positive slope for the electric field because the space charge is a positive constant. Okay, and then you can see actually they meet in the center because the electric field has to be continuous. So given this continuity, we can actually solve the whole electric field. That is precisely what we did back in solar PV. Okay, so you will see the maximum electric field specifically at the interface between the p-type and the n-type region. Okay, and then you can see that the whole electric field, the overall electric field in the p-n junction is always negative. Okay, is always negative. What does negative mean here? Negative means that the electric field is pointing, in the one-dimensional case, is pointing to the left side. Okay, it's pointing to the left side because if you point to the right side, we denote that this is a positive direction. But if you point to the left side, we designate that this is the negative direction. Okay, and this is exactly what we're seeing here because in the p-n junction, the electric field should always go from positive space charge to the negative space charge. Okay, which is why it's always going to the negative direction. Okay, and then in the p-n junction, we were also interested in the potential. Okay, in the potential. And if you want to go from electric field to potential, again, we have a very simple equation that says that the potential gradient, right, d phi over dx should equal the negative of the electric field. Okay, it should equal the negative of the electric field. So since the electric field is negative, in our case, so the negative of the electric field here is going to become positive. Okay, it's going to become positive, and that will give you actually the potential. The potential is always going to increase throughout the p-n junction because the slope is always positive. Okay, the slope is always positive, and then you can see that from actually the slope of the potential, right, is actually small, starting from here, right, because the electric field here is relatively small. Okay, and then the slope will reach the maximum point specifically at the interface. Okay, we have the maximum slope here for the potential, and then after this point, the slope will decrease again. Okay, the slope will decrease again because the electric field is coming back, is becoming smaller, and is reducing towards a zero electric field. Okay, so that will give us actually the potential here. Okay, that will give us the potential here. And then, actually that is only the electric potential, but for semiconductor physics, for understanding the semiconductor behavior, typically we would like to know what is the scale for electron energy or electron potential. Okay, that is actually more relevant to us because most of the time we are dealing with the with electron. Okay, so if you want to go from potential, right, to energy, you just have to multiply by the corresponding charge, amount of charge. Okay, amount of charge. So we know that the electron, the amount of charge is precisely, the electron charge. But then electron carries negative charge. Okay, so for the electron energy, it has to equal negative electron charge, elementary charge, times the potential phi here. Okay, so what we are seeing from here, the potential profile is going to be inverse actually for the electron potential. Okay, so instead of increasing potential in the p-n junction for electron energy, it's going to always decrease from the left side to the right side. Okay, so this means that the electron energy across the p-n junction, it will have a higher energy on the p-type side, but then on the n-type side, the electron energy is going to become lower. Okay, it's going to become lower. It is lower on the n-type side because remember, on the n-type side we have a positive space charge. Okay, we have a positive space charge, so electron is always attracted to the n-type side. Okay, and if electron goes in this direction, because of the positive space charge, because of the electric field, obviously the electron will be losing energy on the way. Okay, it will be losing energy going from left to the right side. So that is basically what I think our physical picture from solar PV. We talk about the p-n junction in the equilibrium in the steady state. Okay, we talk about the net charge, the space charge density. We talk about the electric field profile, which is a linear profile, and then we talk about the potential. So from the linear electric field to the potential, this is going to be a second order function actually in this part. Okay, this is a second order function here. And then from the potential, we do a simple flip to find the electron energy, which is the final curve we have here. Okay, so that is actually a very quick revision for our p-n junction physics back in solar PV. Now, one thing we didn't discuss exactly in solar PV is that how do we go from this physical picture here to an actual solar cell in operation? Okay, so what is the missing condition? So how do we go from the picture we're seeing here to an actual operational solar cell? What is missing? Any additional condition we should add here? And by the way, just want to mention that the calculation we did here for the picture here is using the so-called equilibrium assumption, equilibrium condition. So this means that the picture you are seeing here specifically means a p-n junction in dark condition. Okay, so without any light excitation. Okay, and then also we assume that it's actually in a steady state. So things basically have settled for this p-n junction. Okay, things have settled for this p-n junction. We have a stable p-n junction here. Okay, so obviously, if you want to go actually to the solar cell state, one very important factor is actually the dark condition. Okay, we have to apply the light illumination here so that we can actually see what's going to happen in this p-n junction, which means that we have to apply a sort of excitation on the picture here. Okay, and if we apply the illumination here, then basically we need to introduce additional parameters so that actually the solving will be exactly fit to the real situation. Okay, so what will be the additional parameter we have to introduce here? Let's go to the next slide. Okay, so let's actually summarize what we have so far, and also we introduce the new parameters here so that we can see the difference from a p-n junction in the dark to a p-n junction operating under illumination. Okay, so first of all, we can combine actually the drift and the diffusion equation we saw before. Okay, because for solving the p-n junction before, we didn't actually use these two equations. But right now, if we introduce illumination, we're going to expect the additional drift and the diffusion current, and that's why we have to actually use them for solving the equations here. So if you talk about whole current, okay, if you talk about current from the whole carrier, then obviously any kind of current will be the summation from drift plus diffusion. Okay, it's going to is going to, so you can basically write the whole current, the total whole current will equal the drift whole current plus the diffusion whole current. Okay, and specifically, the first term is the whole drift current. Okay, and the second term is the whole diffusion current. Remember that we have this negative sign here from the whole drift diffusion current, because actually the whole will go from high concentration to low concentration, right? And because of the gradient here, if you want to match the direction of the whole current, you have to add this negative sign here. Okay, and then we can do the same thing for electron current. Okay, we can do the same thing for electron current. Electron current will be the summation between the electron drift current and the electron diffusion current. Okay, so again, there is a positive sign here for electron because the holes in the electron, they have opposite signs. Okay, they have opposite signs. So that is basically the two current or current density we have here. Okay, so remember that the J here indicates that this is a current density unit. Okay, it is a current density unit. And then to solve for solar cells, a very important equation we have to use is the so-called continuity equations. Okay, it's a set of equations that's called the continuity equations. What does continuity mean? Continuity equation basically means that if you focus on a small part in the semiconductor in the space. Okay, so for instance, we're looking at a very small segment of material from X to X plus dx. Okay, so this is a very small region, a very small volume here, and essentially, if we look at hole or if we look at electron separately, we would like to we would like to do a counting of holes and the electron going in and coming out and disappear in this small volume. Okay, the thing is that in the end, if we count all the electron that's going out and all the electron that's disappear. And then we also count how many electrons we are generating in this small volume, and versus how many electrons that is also going out because of the current. In the end, you have to make sure that the positive and the negative they match. Okay, so how many goes in, how many goes out? Eventually they have to fit, right? They have to fit. You cannot produce electron from thin air. You cannot make electron vanish without any kind of phenomenon. Okay, so that is basically the concept for continuity equation. So let's look at one of the continuity equations here. Let's look at the electron here, for instance. Okay, so we are taking the electron density in this region, right? So this is the N. N stands for electron concentration. Nx means that this is the electron concentration in this small volume. Okay, so the N over dt, what does it mean? It means that the overall in this small volume, the electron, concentration difference over a small unit time, dt, right, will have to equal something, will have to contribute, will have to actually come from several contributions. Okay, so what are the major contributions that will change the electron concentration in this small volume? Well, we talk about actually several phenomena from before, right? So one of them is, of course, the electron current. Okay, the electron current. If you have a certain magnitude of electron current going through this small volume, obviously, the larger the current you have, obviously this will contribute to the concentration of electron actually in this small volume. Okay, if you have a larger electron current going in, then obviously the number of electrons in this volume, you will have to increase over time. Okay, you have to increase over time. So we are taking the current here, and then we are comparing actually between the current at the at the x and the current at the dx. Okay, x plus dx. So we want to see what is the difference, between actually the two current densities we're seeing here, right? Because the difference here will be precisely the number of additional electrons that is remaining or that is coming out from this small volume. Okay, is this okay, guys? All right. And then, what are the other possible factors? One of them, obviously, should be the recombination. Okay, should be the recombination. If you have, imagine that if we have electrons actually being recombined in this volume, obviously the number of electrons, it will decrease. Okay, the number of electrons will decrease. So that's why we designate the U here or R here, because here we're using the letter R in the picture. That is going to be the recombination rate. Okay, recombination rate. So how many electrons will disappear in the duration of time dt. Okay, in the duration of the time dt. So that is the recombination rate or recombination velocity here. And then for an actual solar cell, remember that if you have a light incident on this part of the PN junction, we may also see additional electrons being generated. Okay, that is that is basically the carrier excitation that we talked about earlier. So G here, uppercase G here, is the generation rate. Okay, it is the generation rate. It basically means that how many additional electrons we are generating from this small volume because of the light excitation. Okay, so to do a complete accounting, we have to consider all three parameters actually in the statistics in the continuity calculation. Okay, and only if we combine all three can we say that we can make sure that we are not missing any electrons actually in the counting, and we can do the same thing for the host. Okay, we can do the same thing for the host, and the whole continuity equation will be very similar. Except for some minor, sign differences. Okay, except for the sign differences, because again, here this is talking about the current, and then we have to think about, what does the current change indicate in terms of the number of holes, right? Is it meaning we're increasing the number in holes, or does it mean that we're decreasing the numbers in holes? So that's why they have a different size for electrons and holes. Okay, so it should be relatively straightforward for you to see here the reason for the different size. Okay, and then from before, when we talk about the equilibrium, condition and the steady state condition, obviously, if you want to use the continuity equation, it was actually singular back then, because obviously, the number of electrons and holes they are not going to change over time. Okay, unlike a excitation state. But for steady state, we used to have dp over dt and dn over dt, they should equal 0. That is the previous scenario. Okay, and then we can go. We also have to use the previous Gauss law, right? In the differential form, the gradient for electric field will equal the space charge. Now, since we're talking about n and the p here for electron and the hole concentration, at any specific point, right? At any specific point in the PN junction, we have to think about from where we are getting the number of charges. Okay, from where we're getting the amount of charges there. So for the amount of charges we are seeing, obviously we have to use the whole concentration, because that is giving us a positive space charge, right? Minus the number of electrons, right? That is giving us a negative space charge. And then if you have a donor if you have a doping at a certain part, the donor actually will also provide positive space charge. Okay. Well, we have also acceptor. If we have acceptor in this part, then we also have to count the number of acceptors, because supposedly they will be giving us negative space charge. Okay, so that will give you a more complete picture actually compared to before. Now you take into consideration all the different sources for the charge density. Okay, for the charge density. So that is basically the equations we have to use. Okay, we have to use. We will talk about the recombination rate and the generation rate actually very soon. Okay, how to express the U and how to express the parameter G here.
Doctor?
So in summary, let's try to summarize a little bit. If you want to solve for a working solar cell, okay, typically you have to start from these 5 basic differential equations. Okay, so this is the current equation we just mentioned, right? The contribution from drift and the diffusion current, and you have actually 2 equations, one for hole and one for electron. Okay, and then we have the current continuity equation. Okay, the continuity equation. Basically, we're trying to count all the possible sources for the electron or the hole concentration difference. Okay, and finally, we have the modified version of the so-called Poisson equation. Okay, that is basically counting the charge density at any specific point, taking into consideration of hole density, electron density, and the doping concentration, because that is usually producing the stationary space charge. Okay, and lastly, there is a very useful equation for us that is called the Einstein relations. Okay, Einstein relations. So in the equation here, we're seeing this parameter, the mobility, the diffusion constant. Okay, it seems that these parameters are separate entities, they're separate parameters. However, based on Einstein relations, actually the mobility is related to the diffusion constant, right? The drift and the diffusion, they are related to each other. They are related to each other specifically by this ratio. Okay, so the diffusion constant over the mobility of the same carrier, it will equal the same ratio for the other carrier, and this ratio is a constant, which becomes kT over Q. Okay, kT over Q. So that is also a very useful equation for us if we want to solve these fine differential equations. Okay. So now the missing part is just that we have to find the expression for the recombination and the generation, right? Because so far these recombination and generation rate, they are basically unknown parameter to us. Okay, they're unknown parameter to us. So to solve them, we need to take some approximation. Okay, we have to take some approximation. So first, for the generation rate, the generation rate capital G here, typically this is the expression we use to approximate the generation rate. Okay, so what does it say here for the equation? Generation rate equals absorption coefficient. Okay, this is a very familiar parameter because we just talked about absorption coefficient from last time. Okay, so it's the same parameter here, and then multiply by a constant that is the photon flux at the surface. So basically, n0 basically tells you how many photons we have actually at the material surface. Okay, at the material surface, and then if you multiply by the absorption coefficient, we will basically translate the number of a photon into a number of carriers we generate from here. So that is why we have a generation here. Okay, and then the exponential decay term is related to only the depth of the material. Okay, the depth of the material. So at the zero depth, if x equals 0, then essentially we only have a generation equals absorption constant, absorption coefficient times the surface number of photons. Okay, but then as you have a non-zero depth, then this becomes basically a exponential decay. Okay, a exponential decay, and this part is actually very similar to our discussion from last time. We were saying that the irradiance inside the material will follow an exponential decay, and the exponential decay is exactly the same term. Okay, it is exactly the same term, exponential negative absorption coefficient times the depth. And here is the same thing. We assume that the number of photons, it will decrease as we increase the depth. Okay, and then multiply by the absorption coefficient, we can find basically we can estimate the number of carriers that we are generating, right, from the semiconductor. So that is how we find the generation rate. Okay, the generation rate. So that's one parameter down for us. Now the remaining second parameter is to find how many electrons and holes will be recombined in a certain space volume. Okay, that is finding the recombination rate capital U here. So using some assumptions, I'm not going into detail for these assumptions, but specifically we have to use a so-called low injection conditions, right? And then we have to assume a couple of things, for p-time and for n-time material. But typically, these assumptions are easy enough to understand. Okay. And then we have to also see that typically the recombination behavior, it is determined mostly by the behavior of the minority carrier. Okay, it is determined by the behavior of the minority carrier, because usually we have a majority carrier, we have a minority carrier. Remember, recombination is always coming from two different kinds of carriers. But then typically it is the fewer carrier type that is going to be critical for the recombination behavior. Okay, so for instance, if you look at the p-type semiconductor, okay, the recombination rate typically is only related to the electron recombination behavior. Okay, because for a p-type material, the electron is the minority carrier. So what are the parameters we are seeing here? The delta M, right? It is basically the difference from the current electron concentration versus the intrinsic intrinsic electron concentration. Okay, so this means that compared to the intrinsic state, the more electrons you have in this location, then obviously this will increase actually the recombination rate. Okay, and then down here we have the letter tau here. What is the meaning of tau here? Tau is actually the minority carrier lifetime. Okay, so it has a unit of time, and the lifetime here basically means that how long can the electron, exist in this part before being recombined, before its disappearance. Okay, so the longer lifetime you have, it means that your recombination is actually becoming slower, because it takes typically longer time for this case, for the recombination actually to happen. So obviously the recombination will be very slow. Okay, so that is actually something you can see here for the very interesting actually for the recombination rate. It's related to the things actually we mentioned before. Okay. So that is actually the recombination rate expression. Typically, we can use to solve actually the solar cell material or the solar cell p-n junction. Okay, we have actually another parameter here that we need to introduce that sort of represents actually the diffusion behavior in a certain semiconductor. Okay, that is actually the diffusion length. Okay, diffusion length. So if you remember from before, after the excitation. Okay, after the excitation, we said that these electron and the whole pair, they have to actually diffuse over a certain distance before actually they can be actually separated, before they enter the space charge region. Okay, so what would be the maximum difference, or what is the average distance that this electron and whole pair they can move actually before being recombined? This concept is the diffusion length. Okay, is the diffusion length. So diffusion length represents the average diffusion distance a generated carrier can travel until recombination. Okay, so it's also related actually to the recombination rate, right? To the recombination rate, because you can see that the faster the recombination rate, basically it's more easy for the carrier to be recombined, and therefore you will have a lower diffusion length. Okay, so this relation is reflected in the equation here. We have the same tau here for the diffusion length equation. Okay, so if you have a faster recombination rate, it means that your carrier lifetime is going to be shorter, and therefore your carrier can only travel short distance before recombination. Okay, and then we also have the diffusion coefficient here. So on the other hand, for some material, it is actually very efficient for the carrier to diffuse inside. They can actually diffuse long distance before actually any kind of a recombination. So the larger the diffusion coefficient you have, then the longer the diffusion length. Okay, so that is another thing you see here directly. And then don't forget that we have the square rule here, right? To basically to convert into a average diffusion distance. Okay, so we may have a diffusion distance for hole, another diffusion distance for electron. Okay, and typically for silicon, for intrinsic silicon, the diffusion length is between 50 to hundreds of micrometer. Okay, so we need to introduce the diffusion length here, because in the final solution, we will have to substitute the diffusion length into the solution. Okay, so that you can see directly the physical meaning of the equation. So now we're going to skip the solving here. Okay, I hope that this is okay. You can actually find the more detailed solution, I think, in our textbook. But in general, we just want to show you that after we discuss all of these parameters, what is their relationship versus actually the final equation. Okay, so the final equation typically involves solving actually the electron density in the space, the hole density in the space, and so on and so forth. But usually from there, we would like to also calculate the current density throughout actually the space. Okay, the current density throughout the space. The current density throughout the space obviously equals the electron current plus actually the hole current. Okay, that is the total current density. And if you combine actually the solution we have here, you'll find that this actually conforms to a very familiar form actually we saw from before. Okay, we're going to see basically a chunk of parameters here that follows by exponential -1. Okay, and then we're going to see another constant term here, that everything here is inside is a constant. It's independent of voltage, right? It doesn't depend on the voltage. And basically we have a Q generation rate, we have the diffusion length, we have the carrier lifetime, and etc. Okay, so actually this is precisely the same form we have been using in solar PV, right? This is actually will seem them much more familiar to you, right? But if you compare between the two, they are essentially the same. You know, basically the saturated current density, basically it is this part. Okay, well, our familiar I short circuit or J short circuit, the short circuit current density, it is coming from here. Okay, it is coming from here, and that is how we obtain the saturation current density and the short circuit current density. We didn't explain actually from where we got them actually before, but here you can see that directly the saturation current density and the short circuit current density, they come from these several physical parameters. Okay, for instance, if we focus on the J short circuit, okay, you can see that it's proportional to generation rate. So the more generation you have, for instance, the higher absorption coefficient you have, then in this case, actually the generation will become larger, and therefore the I short circuit is going to become larger, right? This actually fits with our perception. Okay, if you have a better absorber, then you can generate potentially more short circuit current density. And another thing is that you have to consider the recombination behavior. Okay, the recombination behavior. If you have a very fast recombination rate, then obviously the lifetime of carrier is actually going to be very small. Okay, so more recombination equals less tau. Okay, and if it's a less tau, then it means that your I short circuit is going to decrease. So the more recombination you have, the less the photocurrent that you can get actually from the same solar cell. Okay, so this is actually very helpful for us. And then we also have the diffusion length. So if you want to have a larger photocurrent or larger I short circuit, then the diffusion length typically has to meet a certain standard. Okay, you cannot have a solar cell that the diffusion length is too small, because this will mean that you are going to lose a lot of photocurrent. So all of this is actually very useful for us to understand the solar cell behavior. Okay, and here we show actually a typical solution from the total current. Remember that the total current is coming from the summation of the whole current, right, at any point plus a electron current. Okay, and if you notice, the total current is always the same, because supposedly the total current density has to be continuous throughout the PN junction under the illumination. Okay, so under illumination, we have a constant current density across the PN junction, but at the different spots, at the different points, we have a different hole and the electron current contribution. Okay, so inside the spatial region, you can see that actually the hole current and the electron current, they are constant. But then if you go far away from the PN junction, the hole and the electron current, they will actually change. But the summation is always the same. Okay, the summation is always the same. So that is actually something actually very, it's very helpful actually for you to know. Okay. So do you guys have any questions so far? Are we following the explanation here? Everything is okay? All right. If that's okay, let us go further a little bit. I would like to talk a little bit more about the recombination losses. Okay, recombination losses. We just see actually from the solution here that the recombination is actually a big part for the solar cell performance. Okay, it affects directly the major parameters that we can get actually from the solar cells. So what are the possible mechanisms for the recombination losses? If we lose electrons and holes due to recombination, what are the possible options? What are the possible routes? Okay, so first of all, we have the so-called bulk recombination. This typically means that this kind of recombination, it happens actually in the bulk of the material, inside the material. Okay, and inside the material, we may have these so-called recombination centers. So basically, if you have a chunk of the material, okay, and inside, if you have a specific point that you have the tendency to lose electrons or lose holes here for recombination, then this typically is the so-called recombination center. And typically, there is another name for this. We also call them actually traps. Okay, carrier traps or electron traps or hole traps. Okay, so from where we can get these kind of recombination centers, typically they can come from first of all fluorine atoms. Okay, if most of the material is based on silicon, but then if you have for instance a very typical occurrence is actually the dopant. Okay, then the dopant itself can be considered as a fluorine atom because it introduced a different crystal structure into the silicon lattice. Okay, and around this dopant, it's actually very easy for you to lose electrons or holes due to recombination. And then another type of traps or recombination centers, it is coming from the so-called crystal errors. Okay, so this actually depends on the material quality. We talk about the purity of the material. We talk about whether we have a single crystalline silicon or multi-crystalline silicon. So the crystal arrangement may have a different orders of a degree, different degrees of order. Okay, if you have a highly ordered material, then you are going to see less crystal errors, meaning that you have a less displacement of the crystal lattice. So that for instance, if you have a pure monocrystalline silicon, then basically you have a very minimum crystal displacement or crystal defects. Okay, because practically the whole silicon wafer is within the same crystal grain. So basically they always follow the same arrangement, the same structure. But then if you compare to a multi-crystalline silicon, you may have different grains, and between the grains, remember, we may have grain boundaries. Okay, and at the grain boundary, you have a crystal displacement. You have the bonds that is not fully in contact with each other. You have defects. The bonds may not be actually may not be connected to another silicon atom. So in those cases, you can say that we have more crystal errors. Okay, and from these crystal errors, we may also have a more bulk recombination. Okay, more bulk recombination. So here we have an example. It's not exactly a calculation example, but this is the idea. Okay, let me go back to the previous slide. So we know that the band gap for silicon it is 1.12 electron volt. Okay, which is very typical for the silicon material. So if you have a pure silicon, okay, if you have pure silicon, and if we want to check for the probability for bulk recombination, probably the recombination is not that easy to happen because for the electron to recombine here in pure silicon, it has to jump all the way down to the valence band. So which means that it has to go over 1.12 electron volt energy difference. Okay, and typically, if you want the electron to go through large energy gap or large energy difference, the probability is relatively small. Okay, but then we sometimes we may see the impurities inside silicon. For instance, sometimes we're seeing impurity from sulfur. Okay, or sulfur atoms, and sometimes there are iron atoms inside the silicon lattice. Okay, so in these two cases, what is the difference in the recombination rate or recombination probability? Okay, if you have a sulfur atoms here, knowing that actually the sulfur atom exists inside the band gap, okay? And it is very close actually to the conduction band, while very far away from the valence band. And differently for the iron, it is sort of in the middle of the band gap. It is almost the same distance to the conduction band versus the distance to the valence band, okay? So which atom will create the more bulk recombination? Actually, it is the iron atoms. Okay, it is the iron atoms. Again, we're talking about the energy difference versus the recombination probability. For this, for this actually a small step here, it's actually relatively easy for recombination to happen. However, if you think about the big gap here for sulfur atom, the probability here is actually quite low. Remember, in the end, the total recombination probability depends on actually the product between the two probabilities we're seeing here. Okay, so the second event is actually very unlikely to happen. So together, the total probability, recombination probability, it will be still very small. Okay, it's going to be still very small. However, for the iron case, we have almost equal distance to the conduction band and to the valence band. So you're talking about basically two jumps that have almost the same probability, and the probability is not too small. Okay, so for the iron, actually the recombination probability, it is actually larger compared to the sulfur atom. Okay, so this is actually the phenomenon that we can expect for the bulk recombination. Remember that if you want to consider the bulk recombination probability or the bulk recombination rate, you have to also see what kind of impurities, what kind of defects we are talking about. And you have to also consider the probability in relation to the silicon band gap model. Okay, so in terms of the electron energy, where are the defects? Where are the traps? And are they allowing a large probability, or because of the energy position, they allow actually only a small recombination probability? Okay, so this is actually something very interesting actually for you to study. If you decide to work on reducing the recombination loss in solar cell. Okay, another kind of a recombination loss is the so-called surface recombination. Okay, surface recombination. So at the surface, we at the surface, typically, if you follow the crystal arrangement here, we know that in the bulk of the material, if you have almost a perfect material here, then most of the silicon here, the silicon covalence bonding, they always have they always find a certain silicon to bond to. They always have a bonding partner. But near the material surface, because you cut off the surface here suddenly, so for some silicon here, some of the covalence bonding here, they don't have any sort of a bonding partner, and therefore you have the so-called dangling bonds, or sometimes we call them the open bonds. Okay, open bonds. Open bonds means that these bonds actually they are in short of one electron, and therefore they are always attracting electrons, free electrons. Okay, so if you generate free electrons and free holes, then the free electron has the tendency to be attracted to the surface. And if they are attracted to the surface, they will get recombined by these bonds. Okay, and this is one of the another mechanism for losses. Okay, another major mechanism for losses. And typically at the surface, you have a very high recombination rate. Okay, you have a very high recombination rate. So the recombination here, typically, it is much larger than the recombination actually in the bulk. Okay, so typically the surface is an additional parameter actually, or the additional consideration you have to include in your design. Okay, you have to see how you can reduce or minimize the surface recombination so that you can have a much better solar cell. Okay, but essentially both bulk and surface recombination, they are important to consider. Okay, they're important to consider because if you want to increase the solar cell performance, you have to work from these two aspects. Okay, so that's why we say that typically to reduce the recombination losses in solar cells, typically you can work from the following angles. First of all, try to decrease the bulk recombination. Okay, by using high quality material, high purity material. and preferably try to use a single crystalline material whenever that is possible. But remember, this is only from the performance point of view. Okay, but remember, in the end, for the for an actual, for a practical solar cell, you also have to consider the cost. Okay, so by using single crystalline materials, yes, we can decrease the recombination rate, but at the same time, is it worth it to use a more expensive material? So these are the things that you have to consider. Okay, and then regarding the surface recombination, what can we do to reduce the surface recombination rate? For these open bonds, we can try to close them by going through the so-called passivation process. Essentially, since we have these open bonds, how about we attach another atom before we actually apply this surface in solar cell? For instance, we can use a hydrogen to close or to attach to the open bonds. In this way, these open bonds or these closed bonds, they will no longer be attracting electrons. Okay, so we will talk about the passivation later, I think, in our chapter here. Okay, but this is one of the other approach that we can use to decrease the surface recombination. Okay, and then before we also mentioned the diffusion length concept. Okay, and typically diffusion length is a very useful parameter to look at the recombination losses. Okay. The recombination, the diffusion length equation basically says that the diffusion length equals the square root of a diffusion coefficient times the lifetime of tau. Okay, times the lifetime of tau. So if you have a very fast recombination, typically it means that your diffusion length will be very short. Okay, so when will we see very short diffusion length? Well, first possible scenario is that you have a lot of defects. Okay, so this includes doping, because doping is introducing fluorine atoms, right? Or if you have imperfect materials, you have a lot of imperfections in the material, a lot of defects. So this actually will give you basically the traps that we talked about before. Okay, from the bulk recombination. And then surface recombination, again, this is the second possible scenario. You may have a lot of recombination losses at the surface. Okay, and then there is a third scenario. Okay, there is a third scenario where you may expect a larger recombination. That is actually the high density of free carriers. So for that, actually, I would like to bring your attention actually to the recombination rate equation we mentioned earlier. Okay, so if you remember, the recombination rate equals the delta of the carrier divided by the lifetime of this carrier. Okay, so even though sometimes we may have the same lifetime, the same tau, but then remember the delta here is actually coming from actually the actual concentration of carrier here minus and 0, which is the intrinsic carrier concentration level. Okay, intrinsic carrier concentration level. So the thing is that this is from the equilibrium state. This is the initial solution for the semiconductor for the concentration of the carrier here, right? When you have an intrinsic the semiconductor. But then, at the if you expose the material to sunlight, if you expose the material to any kind of excitation, then in this location, the number of free carrier, it may increase. Okay, for instance, if we have a very large generation here, then this actually will increase the amount of free carriers that we have in this part. Okay, but then the risk from having a lot of carriers here is that this will increase the delta concentration. Okay, the delta concentration, and this in turn is going to increase the recombination, because understandably, if you have a high density of a carrier here, you have a more chance, you have a larger probability for recombination to happen. If you have a very small number of carriers, then obviously it's more difficult for recombination to occur. Okay, so that is another related factor here. If you have a high density of free carriers present from absorption, from excitation, then this typically will also increase the recombination, and therefore it will decrease actually the diffusion length, because because if you have a faster recombination rate here, this typically will mean that your carrier will only exist for a very short lifetime, okay, and very quickly it's going to disappear because of recombination, and this will give you very short diffusion length that you have here. Okay, so these parameters actually they are related actually to each other in many senses. Okay, in many senses, and this is how we can try to decrease or improve the solar cell performance. Okay, so now I would like us to look at the operation of a typical silicon solar cell. Okay, so this is the same silicon solar cell we talked about back in solar PV, but right now let's just look at different scenarios that we may encounter in this solar cell. Okay, so the picture here basically shows you the cross section of the solar cell. Okay, of the silicon solar cell. Remember, near the surface, typically where we have the emitter. Okay, with the high doping concentration. Okay, with high doping concentration. And in the base material, we have the opposite type, that is the p-type material. The overall solar cell, right, has about 200 micrometer thickness, because here we have a 180 micron, and from the surface we have a 0 micron depth. Okay, and then between the p-type and the n-type, this is where we have the space charge region. Okay, and considering the space charge region, and also with the diffusion length. For the diffusion length, actually for the p-base material is about 100 micrometer length. Okay, so this means that once you generate the free electron and free holes, on average, they can travel actually. They can diffuse across a distance about 100 micron. Okay, about 100 micron. And now we have 4 different scenarios here. Okay, we have photons entering the solar cell, and then they are being absorbed at 4 different locations. Okay, so let's look at actually the absorption scenarios one by one. Okay, depending on where the photon is being absorbed. So for photon number 1, okay, the absorption happens actually at a very shallow place. Okay, happens at a very shallow place. Let me clear things up here. Okay, good. So it is absorbed actually very near to the front surface. Okay, it is absorbed very near from at the front surface, and then from there we generate the electron and the hole pair, as you can see here. Okay, but at this time, remember the electron and hole pair, they're still attracted to each other. They're not free carriers technically. You have to separate them. How can we separate them? We can only do that within the space charge region, because in the space charge region we have a very intense electric field. Okay, so that we can separate them, we can push them in the opposite direction. But then for this electron and hole pair to go to reach the space charge region, first of all they have to diffuse. Okay, because outside of the space charge region, the electric field is precisely 0. Okay, so we have a 0 electric field here. We have a 0 electric field here, and the only mechanism that is available is the diffusion. But then there is a problem. The problem is that in the emitter, right, in the N+ emitter, we mentioned that the doping is actually very heavy, where we have a very high doping concentration. Okay, so this means that actually the diffusion length for actually the electron and hole pair here is going to be very short. Okay, because from heavy doping. Why is that? Because we just mentioned actually the recombination actually equation. Okay, if you have a high difference, very large difference from the intrinsic concentration, such as when you have a heavy doping. Okay, when you have a heavy doping, the carrier concentration here is going to be very high, and therefore you can say that we have a very high density of carriers present, free carriers present. Okay, in this case, actually, this will decrease your diffusion length significantly. Okay, so even though we say that in silicon we may have 100 micron diffusion length, but in the emitter region, the diffusion length is going to be very, very small. Okay, this means that on average, this electron and hole pair here, they can only diffuse very short distance, and immediately they will get recombined. Okay, so can we expect actually, can we expect to generate electricity from here? Actually, this is a very unlikely. Okay, this is very unlikely. Even though the emitter has only 0.1 micrometer thickness, but the diffusion length is actually even smaller. Okay, the diffusion length is much smaller than that. This means that when you generate electron and hole pairs in the N+ emitter, immediately they will be terminated. They will be terminated from recombination. Okay. In other words, most of the time we cannot expect electricity coming from photon number 1, right? Even though it's very easy for you to absorb photons near the front surface, but most of the time we get the zero electricity from there, simply because the diffusion length in this part is extremely small, and they will get recombined immediately after the excitation. Okay, so if you go back to the previous process, right? This means that for photon number 1, okay, we may usually have a very efficient absorption, because in the front surface you can absorb photons very easily. Okay, we may have a very efficient generation process, but then the problem happens for the diffusion. Okay, you have a very low diffusion efficiency, and therefore you will not have actually the following action, the following process. Okay, so that is actually the scenario for photon number 1, which is why typically we also call the N+ emitter region the dead layer, right, in silicon solar cell, because most of the time absorption happening here is not going to contribute to the electricity, to the power. Okay, so that is for the first scenario. Let's look at the second scenario here. For the second scenario, the photons enters deeper into the solar cell, and it is being absorbed directly inside the space charge region. Okay, because it is absorbed inside the space charge region. So in this case, actually, we're skipping. If you go to the previous process, right here, for the second photon, right, we also have a very efficient absorption, right? We may also have a very efficient excitation, okay? And then the thing is that for the second scenario, we are skipping through the diffusion process, because immediately the generated electron and hole pair, they are already under the electric field from the space charge region, okay? And then this means that you may also have a very efficient separation process. And if you have a very smooth collection, then this means that you can generate a lot of electricity from here. You can generate a lot of free electrons and free holes. Okay, so this is a very efficient process actually for the photovoltaic action. Okay, for the photovoltaic action. And we typically say that practically all the generated electron and hole pairs in this region, inside the spatial region, they can be actually, most of them, they can be collected, they can be harvested to generate photocurrent. Okay, so they will contribute very significantly to the eye-short circuit that you are seeing. Okay, so that is the second scenario. And then more commonly, we may have the third scenario, that the photon is entering deeper into the solar cell. Okay, this happens, for instance, if you have a long wavelength. For long wavelengths, they typically they have actually smaller absorption coefficient, and usually for long wavelengths, most of the time they have actually higher penetration depths. Okay, higher penetration depths, and they will enter deeper into the material, and then at a deeper location they will be absorbed. Okay, so if a photon is being absorbed here, then now it's actually basically it depends on the probability. Okay, the probability of what? The probability of these excited electron and hole pair, whether they can diffuse actually to inside the spatial region, or actually they cannot make it to the space charge region. Okay, so for diffusion, we know that the diffusion depends on the concentration gradient. Okay, so in the base material outside of the spatial region, here we have a certain, we have a certain hole density, right? But in the spatial region, the hole density is practically zero. Okay, it's practically zero because this is the depletion region. So overall, the diffusion direction is towards the space charge region. But then, depending on the diffusion behavior, they may not go in a straight path. Okay, they will go in a sort of a semi-random path. But in general, it is going towards the space charge region direction. But then now, this is where the diffusion length becomes important. Okay, the diffusion length, for silicon, if we assume that the diffusion length is about 100 micron, then depending on the location of the absorption, if the absorption location is very near to the space charge region, then you have a high chance of the electron and hole pairs diffuse into the space charge region. If they can reach the space charge region, then immediately they can be separated. Okay, they can be separated. So holes actually will go down and electrons will go up. And in this way, you have a very efficient, generation of currents. Okay, but then there is also certain chance that even though you have a diffusion from the electrons and holes, but then because of the limit of the diffusion length, some of the electrons and holes, they may never reach the space charge region. So in those cases, the electron and holes basically will be lost. Okay, they will be lost due to recombination, and from there we cannot get the electricity. Okay, but within reason, we say that typically within the diffusion length from the space charge region, in this region, absorption in this region, there is a certain chance for you to generate electricity. Okay, to generate electricity from there. And the probability typically is quite high because you have the absorption takes place within the diffusion length. Okay, so on average, we can expect that the electricity can be generated from here. Okay, what is the opposite scenario? The opposite scenario is for absorption to happen beyond the diffusion length. Okay, so for absorption happening here, even though they may diffuse, but most of the time, because of the diffusion length limit, they are actually far away from the space charge region. So for these electron and hole pairs, no matter how they diffuse, typically they can never reach the space charge region. Okay, in those cases, these carriers will be completely lost due to recombination. Okay, it will be lost completely due to recombination. And what about the photon energy here? If they lose the photon energy, where does this part of energy go? Typically, after recombination, you generate actually thermal energy. Okay, you can generate some sort of thermal energy in the crystal, so that actually the end result is that the crystal or the material, it will become slightly warmer, but nothing more. You cannot get electricity from here. Okay, that is because you have a very minimum diffusion efficiency. Okay, you have a very minimum diffusion efficiency here. So these are the four possible scenarios we can expect from a typical solar cell. Okay, from a typical solar cell. Right. So you can see. Yes, go ahead.
So the distance between 100 micrometer and 180 micrometer is not very useful to us. So
Exactly.
why don't we remove it? Or is this the limit of how we can cut silicon?
Remember that the absorption behavior is related actually to also the wavelengths. Okay, the wavelengths. And then here, yes, we're making this more than the diffusion length, but also the diffusion length will change for different carriers, for different specimen. Okay, so there is a reason that we make this a slightly covering more than the diffusion length, because remember the diffusion length only represents the average diffusion distance. Okay, diffusion distance. So we can still expect, let's say, a certain portion of electricity, let's say from very close to this part. But then yes, very far away from that, we do not expect a lot coming from the excited electron and hole pairs. Okay, but then why are we making this thicker than that? It is because for silicon, actually, overall, silicon has a very good behavior overall. So even if we make this a little bit thicker, it's not going to be a major, difficulty actually for the silicon solar cell. Silicon typically has a relatively small recombination loss compared to other kinds of materials. And later, if you once we talk about other generations of solar cells, you are going to see that the diffusion length is becoming more critical here. Okay, but for silicon case, even if you increase it beyond the diffusion length, the additional loss here is not going to cause you a lot of headache. It's still relatively efficient for that. Okay, this
Okay,
is
thank
okay.
you. Yeah,
No problem.
thank
Okay, so yeah, so if we focus on actually the four different scenarios we talk about here, basically this highlights for you the fact that if you want to achieve the maximum performance, the best performance in the solar cell, what should be the main parameters you should focus on? Typically, we want to have a materials with a high diffusion length, definitely. Okay, the diffusion length should be as high as possible so that we can actually find a better balance between the recombination loss and the absorption behavior. Because remember, in the end, you need a certain value for thickness in order to absorb actually most of the photons. Okay, this is actually especially important if you want to harvest long wavelength photons. Okay, because we mentioned for long wavelength photons, the penetration depth typically is high. Okay, and you need a certain amount of thickness if you want to absorb most of the long wavelengths or infrared photons. But then, this means that you have to expect that the most of the infrared photon they will be absorbed very deep into the solar cell, and then they have to go across even longer distance. They have to diffuse longer distance in order to be separated. Okay, so this is actually extremely important if you want to focus on the infrared spectrum, on the infrared photon. You need to have a thick solar cell, relatively thick solar cell. At the same time, the solar cell diffusion length, it cannot be too small. Okay, it cannot be too small. So that is basically I think the conclusion we can hopefully we can draw from here today. Okay, I have actually a side question for you. So a small question on the side. So assuming that we have an efficient solar cell, typically we are expecting the electrons and holes to be separated. So after separation, what is the next step? After separation, electron will come out from the N-type electrode, and holes actually will go out from the P-type material, the P-type electrode. Okay, so the question is, we are under the sunlight. The solar cell is constantly generating electrons and holes, and they are going out from the device, okay, constantly at a very high rate. So the question is, will we eventually deplete, the electrons and holes inside the solar cell? Because considering we are constantly, generating electrons and holes, and we are sending them out from the solar cell. Okay, so this is actually the question. We have the answer down there, but you can try to think about this for a small while. Okay, the answer obviously is that we are not going to deplete the holes and the electron eventually, because remember, eventually holes and electrons, these two concepts, they are just invented to talk about the movement of the electrons. Okay, so what are electrons essentially? Electrons are the free electrons, right, in the conduction band. Okay, in the conduction band. And what about holes? What are holes? Actually, we invent the concept of holes to talk about electrons, but in the valence band. Okay, so holes eventually are the electron vacancy in the valence band, and we define that this is a hole. Okay, so specifically, holes moving in one direction equals electron going in the other direction, but in the valence band. Okay, in the valence band. So the question is, are we actually removing electrons from the semiconductor? Are we removing holes from the semiconductor? Not exactly, because after the electron goes out from the circuit, into the circuit, they will basically they will lose their potential at the low. Okay, so a high potential electron, right? The typical definition for electron, it will relax actually to low potential after the low. Okay, after the low, and then this electron actually will come back to the semiconductor. Okay, how do we know that this is coming back to the semiconductor? Because actually we have a hose from the p-type side going in the opposite direction, so that this is equivalent to the electron going in the other direction. Okay, so if you look at the electrons and holes in this way, you can see that actually we're sending our high energy electron to the low, and then after the low, the electron is actually switching to the low potential state. And in the low potential state, the electrons are coming back to the semiconductor. So this forms a complete loop for the solar cell operation. So in this way, we will never run out of electrons and holes. It's always electrons. Okay, it's always electrons, and we are constantly regenerating the electrons, by having the loop in the circuit. Okay, so this is actually the idea for understanding better, the electron and the whole concept. Okay, I hope that this is clear with you. Okay, you can read more about this in the slides here. Okay, so I think that's it for today. We're going to leave one concept to talk about later next time. That is the external quantum efficiency. Okay, just a very quick sentence before we wrap up today. So since we talk about all these physical process here, we would like to actually have one parameter that represents the overall conversion efficiency, and that will be our external quantum efficiency. Okay, so remember this external quantum efficiency, essentially, it is the product of all the process we mentioned before. So the absorption efficiency, the excitation efficiency, the diffusion efficiency, etc., etc. Okay, and the total product is the so-called external quantum efficiency. And the thing is that this is something we can measure for our solar cell, and it will be very useful for us to do further study on the solar cell. Okay, so yeah, sorry about the delay, but yeah, thank you very much, guys, for attending today. Do you have any further questions before we dismiss the class? Is everything clear for today? Okay, yeah, excellent, excellent. So thank you very much, ladies and gentlemen, and I'll see you next time. Okay, thank you. You can log off now. Thank you very much.